In this example, we could consider a more advanced differential equation of the form dy dt is equal to some function of y with a parameter alpha. The specific form of that function g sub alpha of y is y cubed minus alpha y, which, according to here, the other right-hand side factors as factor out the y squared minus alpha. Okay. Always a good idea when you're trying to wrap your mind around a new differential equation with parameter, so trying to get into a bifurcation plot. A good idea just to try a couple values of alpha. There's several obvious candidates here. Alpha equals 0 is usually an interesting one to look at. So g sub alpha 0 for alpha of y is y cubed. Okay. You then want to find equilibrium solutions, okay, which turn out to be y is equal to 0. So g sub 0 evaluated at 0 is 0. So that's an equilibrium solution. Drawing the phase line then means that you have one equilibrium at 0. When y is bigger than 0, you get a positive number, and when y is less than 0, you get a negative number. So here we have a source at y equals 0. Okay. Always then interesting to ask yourself what happens for maybe a positive value of alpha or a negative value of alpha. So if we try that now, just choosing kind of one at random here, how about alpha is equal to 1, which means that g sub 1 of y is equal to y cubed minus y, or y times y squared minus 1. Which means that now there are 3 equilibrium solutions at 0 and at plus or minus 1. Okay. Which then lead to phase lines, okay, of the form 1, 0, and negative 1 for y, and then we have to decide on the plus or minus signs. That should be readily available when you plot for alpha equal 1, the right-hand side, g sub 1 of y as a function of y. So you'll get a 0 here and a 0 at 1 and negative 1. And when y is between 0 and 1, y is positive. Y squared minus 1 when y is between 0 and 1 will be a negative number. So the graph has to be down here and then come up and turn like this. So here's a graph. And therefore, when y is bigger than 1, we have arrows that point upward between 0 and 1 in this region. The right-hand side is negative, so the arrows point down. Between 0 and 1, they're positive, and less than negative 1, negative again. So we're seeing y equals 1 being a source, y equals 0 being a sink, and y equals negative 1 is a source again. Okay, so there's something interesting to determine about the value alpha equals 0 and the case alpha is equal to 1. So we've tried 0 and a positive number. Maybe a good idea to try a negative number then. We'll do that in, say, red over up here, or maybe here on the side. Keep it all on the same slide. When alpha is negative 1 then, g sub negative 1 of y will be y times y squared plus 1, and therefore you have only one equilibrium solution again at y is equal to 0. There's only one. Y squared plus 1 will never be 0, so there's only one equilibrium coming from y equals 0. So we're back to 1 equilibrium now, okay? But the fact that that y squared plus 1 is positive, we now have positive, and we have still again negative. Okay. So, putting all this together into something called the bifurcation plot is, well, relatively simply a matter, or at least a matter, of trying to turn these 3 separate examples, or as many examples as you needed, to plot something in the y alpha plane. Okay, we can see here that our examples say that when alpha is negative, okay, every time alpha is negative, in this case it was -1, but anytime alpha is negative, you're going to have equilibrium, but only one of them. So each time there's only one equilibrium, okay, a whole line of them. And they will, for each value, the arrows would be pointing upward and upward and upward, okay, even when the y value is less than 0, the arrows are pointing up also. Okay? So that's what we get from the alpha being negative case. When alpha was equal to 0, there was again only one equilibrium, okay, and the equilibriums were pointing like this, I believe. Oh, sorry, up and, oh, Jason, sorry. The arrows down here, I'm sure you caught this, these arrows should be pointing down. Okay. Sorry about that. And the blue arrow below is also pointing down. Okay. Then we went to the alpha was greater than 0 zone. Alpha greater than 0. And all of a sudden 3 equilibrium appeared, no matter the value of alpha. And so we have now 0 being an equilibrium, and there appeared 2 others. Okay. And so we have a bunch of equilibria at 0 for every value of alpha, and then there is 2 equilibrium, okay, and they get larger and larger. We'll see that in a graph if you prefer that each values get, the equilibriums get to be a larger value of y. We can then draw one of these phase lines, for example, that is going to turn positive, negative, okay, negative for 0, and then on the other side of 0, because 0 in this case is an equilibrium, they point upward and then downward below the equilibrium. Okay. So this is a rough sketch, and if one were to try to draw this a little bit better, okay, one could see that we have equilibria along this line. You have an equilibrium still here, and then there is this shape that was created, the pitchfork, so to speak. Along this branch of the pitchfork, we have sources. Along the bottom branch, it looks like we have sources. Okay. Here we had sinks, right? So this is what the pitchfork looks like on the alpha greater than 0 side. On the alpha less than 0 side, our sinks switched to sources. And that's what our bifurcation plot looks like for various values of alpha in the phase line y. Okay, we can look at a plot of this behavior. Okay, Let's see if I can make this plot a little bit bigger. Let's see if we can compare, see if what behavior was happening in the plot of the slope field. So y is a function of t. In this plot, the x-axis is t and the vertical axis is y. So for various values of mu, when alpha was less than 0, right, we had solutions going away from the equilibrium. Here you can see the equilibrium solution 0. Solutions were going away and then away. So that was a source. But something happened at 0. Okay. At 0, from 0 to 1, it looks like nothing is quite happening. Right? We're getting one. You can kind of see it in here. Let me draw some more streamlines. Okay, something's interesting happening somewhere for this new value of mu. Looks like we had 2 equilibrium. Okay. Some of the solutions go away and then away, so we have a source. And then this equilibrium at 0 switched to a sink, because all the solutions are getting funneled in time to the equilibrium y equals 0. And for values below this second equilibrium, the solutions are going away. Okay, so that looks like that behavior happens, right? We're looking at this. I think that behavior switched at a certain point. We'll have to look at our bifurcation diagram, but here there's something interesting happening. Solutions going away. It's kind of hard to see the equilibrium, but they get more and more pronounced. They get bigger and bigger and bigger. Now the equilibriums, we can see them kicking in this region right here. It's kind of hard to make out what's going on in the slope field, which is why it's sometimes good to go ahead and just look at the right plot of the right-hand side of this differential equation. You can see that for when mu is 0, it's y cubed. When y went negative, there's still only one equilibrium solution at 0. But right here, when mu gets positive and more positive mu, there's now 3 equilibrium solutions, but 0 is always a solution. So this is where the pitchfork happens. Okay, and then you can see in this bifurcation diagram, here's the pitchfork nature. Okay, when mu was less than 0, okay, there's only this line of equilibrium, and then you could look at the previous graph to assign pluses and minuses to this line for up and down arrows. When mu got to be a little bit bigger than 0, all of a sudden we now had 1, 2, 3 equilibrium values for all values of the parameter greater than 0. And in the slope field, it was really hard to make out in this region. Right in this region, there were 3 equilibrium, but they were so close to each other, it was really hard to make out what was going on. But the bigger mu got, the more pronounced, the farther you move on this pitchfork, the larger the new equilibrium are, and the field starts to spread out, and you get sources and then a sink here at 0. So that completes this more difficult example, and I will leave you to look at the problems in the textbook for additional examples.